Now, when it comes to matrices for transformations, you'll kind of have two options. Sometimes they will tell you what the transformation is, and you will have to work out what the corresponding matrix is, which we're going to do now. Sometimes you'll get given the matrix and you'll have to work out what that transformation is. The best way of doing both of those is to consider what happens to 2 points in the xy plane. So the points we're going to consider are 1, 0, or the vector 1, 0, and 0, 1, or the vector 0. Okay. And I'll usually call these point A and point B. Okay. So I'll show you how to use these to figure out the matrices here. You can just kind of go backwards to work out what the transformation is from the matrix. You'll see that later. Okay. So we're starting out with a reflection in the y-axis. So if I start out with my points A and B, if I reflect these in the y-axis, A gets reflected over here. And I'll put the image of A, so A dash over here. And B is on the y-axis. If it gets reflected in the y-axis, it stays where it is. That's B dash, that's the image of B. So we can say that the point 1, 0, the vector 1, 0 goes to minus 1, 0 when it gets reflected in the y-axis over here. And the point 0, 1 or vector 0, 1 stays at 0, 1. All you do is you write these 2 points or these 2 column vectors in a matrix. So the transformation matrix is 1, 0, 0, 1. Okay. Always starting with A and then B. It kind of starts off from the matrix 1, 0, 0, 1. Okay, and that's the transformation matrix representing a reflection in the y-axis. For reflection in the x-axis, again, if you start off with A and B, reflecting those in the x-axis, A stays where it is. So 1, 0 goes to 1, 0. B gets reflected down, so the image of B is down here at 0, minus 1. And so you can write these in a matrix. The 1, 0, 0, minus 1 is the transformation matrix for a reflection in the okay. So if you're given the transformation, write down the vector A and B or the point A and B, do the transformation to it, and then you can work out what that matrix is from there. In this box here, reflection in the y-axis is represented by the matrix minus 1, 0, 0, 1. Here it mentions invariant points and invariant lines, which is something we're going to come back and talk about more later on in this. An invariant point is a point that isn't moved by the transformation. Okay, so reflection in the y-axis, any point that's on the y-axis isn't moved by the transformation, it stays where it is. So that's an invariant point. The invariant points are all points on the y-axis. Any other point would get reflected across. Anything over here, anything over there. An invariant line is slightly different to an invariant point. So an invariant line is any line that doesn't get changed when you reflect it in the y-axis. It's not necessarily that the points on that line stay the same. For example, when you're reflecting in the y-axis, any horizontal line, if you reflect that in the y-axis, stays at that same horizontal line. The points inside that line do change. So like this point over here will get reflected to this point over here. But as long as the points get reflected onto the same line, it doesn't matter. So invariant lines for reflection in the y-axis are all horizontal lines and the y-axis itself. If the y-axis itself, if you reflect it in the y-axis, it's the same. The y-axis happens to be a line of invariant points. So a line of invariant points is also an invariant line, but not all invariant lines are lines of invariant points. For reflections in the x-axis, this is represented by 1, 0, 0, minus 1. Similarly to the reflection in the y-axis, invariant points are anything on the x-axis. And then invariant lines are the lines that don't change when you reflect them in the x-axis. So this is all vertical lines and the x-axis itself. So when you're reflecting in the x-axis, any vertical line here, if you reflected it, it would look exactly the same. And any point on the x-axis, if you reflect that in the x-axis, stays exactly the same. This time we're reflecting line y equals x. So we're going to start off with our a and b again. So a is 1, 0. B is 0, 1. I'm reflecting these in the line y equals x. Okay. So reflecting the line y equals x, A will go over here to where B originally was. So the image of A goes up here. And B will go down here to where A originally was. So the image of B is there. Okay. So 1, 0, A has gone now to 0, 1. And 0, 1, B has now gone to be at 1, 0. They're swapped around. And so the transformation matrix, write those in. 0, 1 first column, 1, 0 in the second column. Like the identity matrix, but with the elements on. For reflection line y equals minus x, let's do a similar thing. Is y equals minus x. So A is here, B is here. Reflecting these in this line, so A goes down here to be at 0, minus 1. B goes down here to be at minus 1, 0. So let's write those in. So 1, 0 goes to 0, minus 1. And 0, 1 goes to minus 1, 0. Transformation matrix for this one, 0, minus 1, 1. So let's write these in here. So reflection in line y equals x, we said, is 0, 1, 1, 0. Invariant points. So for this transformation, the points that don't get changed by the reflection is anything along the line y equals x. Anything on there doesn't get changed. The invariant points are all points on y equals x. Invariant lines is anything perpendicular to that. So invariant lines are all lines of the form y equals minus x plus c. So these are any line that has a gradient minus 1. This one, if you reflected it in that line, it will stay the same. Or this one here, or this one here. Any line that's got gradient minus 1 will get reflected to itself. Well, it doesn't matter where it crosses the y-axis, that's why I put plus c. All of those. And the line y equals x itself is a line of invariant points. And reflection in the line y equals minus x, we said, is this matrix 0, minus 1, minus 0. Invariant points along this are all points on the line y equals minus x. And invariant lines is anything perpendicular to y equals minus x. So this is all lines y equals x plus c. So all lines with gradient 1. This one, but also this one, this one. Anything with gradient 1 will get reflected onto itself. And the line y equals minus x itself. But you can do reflections in any lines. There's a formula for this on the formula book. Now, you've got to be really careful with this because there's two formula on the formula book. There's a formula for reflecting in any line, and there's a formula for rotating around the origin. They look very, very similar, but they are slightly different. Okay, so this is the one for reflection in line y equals tan theta x, and this is the one over here. For the rotations around the origin, they're very similar, so you've got to make sure that you choose the correct one. So this example here, we've been given this matrix, so minus 0.8, 0.6, and so on, and we're asked to describe the transformation. You should look at that and think, right, can I compare it to one of the ones on the formula sheet? And the difference you're looking for really is you're looking for where the minus signs are. So on this reflection one, the leading diagonal has opposite signs, which our one does here as well. If you look at the rotation one, it's the other diagonal that has opposite signs. Okay, so that's what you've got to look for. So all we've got to do is we've identified that this is a reflection. We've got to work out what the angle is to work out what the gradient of the straight line is. Okay. So I'm going to set cos 2 theta equal to minus 0.8. And I'm going to set sine 2 theta equal to 0.6. And I've got to find the value of theta that works for both of these equations. So solve these in your calculator.
I can do no wrong.
So 2 theta equals 143.1. And extra solutions for cos 360 minus that one. 216.9. Then if I divide these through by 2, so 108.4. What you complain about?
I get 3 letters. It's like take it or leave it.
Right, let's do inverse sine 0.6 now, so 36.9. Extra solutions for sine come from doing 180 minus that one. And you can see what's going to happen here. Divide these through by 2. So 71.6 is the one that we want, because that's the one that works for both of them. Just completion sake, we'll divide that by 3, so 18 points. The solution that works for both of them is 71.6. Okay. We'll use this then to work out the gradient of the straight line. So I'm going to delete lines so I get the exact value here. And then if I do tan of that value, it gives me nicely 3. So this is a reflection. In the line y equals 3x. And there will always be reflections in the lines that go through the origin, because remember the origin has to stay invariant for it to be a linear transformation. So the origin cannot move, which only happens for reflections in lines through the origin.
Oh, yay.
So this is one that we've just done. So it's the reflection in line y equals minus x. If you wanted to work out what the transformation was from the matrix, apply it to those points 1, 0, and 0, 1 and see what happens. You can draw them on the diagram and then see, right, there's been a reflection in the line y equals minus x. For the transformation and the coordinates and stuff, so you do the matrix times a, b, that will end up with 3 plus 2, 8, and b plus 1. You can get a pair of simultaneous equations to solve there, and you should end up with a is minus 2 and b. Next transformation we're looking at is rotations around the origin. So you can only have rotations around the origin being linear transformations, because remember the origin has to stay where it is. You can have rotations of any angle, but the standard angles are easy enough to work out. So again, we're going to start off with our vectors. Oh, I'm going to use vectors. Our vectors A and B. The 1, 0, 0, 1. And we're going to draw on this diagram what happens when we rotate these 180 degrees around the origin. So rotating 180 degrees around the origin, A gets moved over here and B gets moved down here. Now notice these coordinates of A dash and B dash, the image of A and image of B, are in the same positions as a reflection in the line y equals minus x. But it's not the same transformation because the opposite way around. It's really important that you label these up clearly, otherwise it's easy to get mixed up between the transformations. So 1, 0 goes to minus 1, 0 in this case. And 0, 1 goes to 0, minus 1. And so if you put these in the matrix, rotation matrix 180 degrees around the origin is minus 1, 0, 0, minus 1. Doesn't matter whether it's clockwise or anti-clockwise because you'll end up being the same. You can obviously do 90 degrees either way as well. So if you've got the points A and B and you rotate these 90 degrees clockwise around the origin, so same way clock goes around. So A goes down here, A dash, and B gets rotated around where A is. Again, notice this looks like the same points for a reflection in the line in the x-axis, but make sure you label these up carefully because they're not the same points. So the point 1, 0 goes now to 0, minus 1. Point 0, 1 now goes to 1, 0. So the transformation matrix for rotation 90 degrees clockwise around the origin is that. You could do a similar sort of thing for 90 degrees anti-clockwise as well.
You have to remember this. I mean,
You can work them out every time. Okay. That's what I do. I don't know mathematics. That's really cool.
I don't.
Now, 45 degrees anti-clockwise. Let's see what happens here. So we've got the 2 points A and B. A will get rotated 45 degrees anti-clockwise, so somewhere around here. And B will get rotated 45 degrees somewhere around here. What we know about these is these are still a distance of 1 from the origin. And let's just look at A first. This angle's 45 degrees. You can use these to figure out the X and Y coordinates of where A is. I mean, in an exam, you'd use the matrix, but I'm doing it now. So if we want to work out the X coordinate, this is the adjacent side. We've got the hypotenuse. Cos 45 is adjacent of the hypotenuse. X is root 2 over 2. And same for the Y. So sine 45 is Y over 1. The Y coordinate is also root 2 over 2. So 1, 0 goes to root 2 over 2. Root 2 over 2. 0, 1 for B. So it's still up root 2, but it's root 2 over 2. It's root 2 over 2 to the left, so it's minus root 2 over 2. Root 2. Okay, but from these you can kind of see. So for A, this was cos 45 over sine 45. Minus sine 45, so cos 45. That's where this rotation matrix kind of comes. Okay, but it's in the formula book, you can just quote it. You don't have to work on it like I've just done. Now you can just go ahead. So a rotation anti-clockwise around the origin to an angle theta is given by this matrix here. Notice the difference between this and the reflection one is where the minus signs are. And obviously this one's theta and that one's 2 theta. Invariant points for rotations around the origin. There's only one, which is the origin itself. Invariant lines depends on the rotation. So invariant lines, only rotations 180 degrees around the origin have invariant lines. Yeah. So for example, basically any line through the origin, this one, if you rotate it 180 degrees around the origin, not quite 180 degrees, no. It looks the same. any line that you draw through the origin, you rotate it 180 degrees is going to look the same. Okay, so when theta equals 180, all lines through the origin, i.e. it's anything of the form y equals mx. Otherwise, there are no invariant lines. Question for you over the page. I'll snip the formula into that book for you. Right, I'll just leave it up there. So have a go at that. To the matrix in the formula sheet. So compare this to the matrix in the formula sheet. You're looking for the ones that have the diagonals that have the same sign and the diagonals that have different signs. It's not about having exactly the same signs. So the leading diagonal here, they're both minus, so they have the same sign. The leading diagonal in this one, they have the same sign. And the other one has opposite signs, so that's the one that matters. Set cos theta equal to minus root 2 over 2. Set sine theta equal to root 2 over 2 and solve and look for the answers that are the same, which is 1, 3, 5. So this is a rotation anti-clockwise around the origin of 35 degrees. Then just multiply this by all of these points. You can do them all together in one matrix if you want, or individually. Make sure you write them as coordinates at the end, though. Those are what you should have got before that. So the second question for you, again, compare this to the matrix from the formula sheet and solve. So you get cos theta equals minus 0.28, and you get sin theta equals minus 0.96. Solve this for the ones that end up being the same. And this is the 253.7. This is a rotation 253.7 anti-clockwise around the origin. You can turn it into clockwise rotation if you really want to.